All right, we're going to look at some limits at infinity here. And I'm going to go through them pretty quickly. I would encourage you to pause the video if you're looking at these when you think you know what to do and try to work them out yourself and then play again. These first two limits right here, these are both rational functions, which if you've taken pre-calc and algebra 2, you've graphed them and you've talked about rules for where their horizontal asymptotes are. And that's what we're talking about when we're talking about limits at infinity, right? As x approaches infinity or negative infinity. We're talking about what's called end behavior. What does the function do, way off toward the right or way off toward the left? And you might remember those rules. The rules are based on logic, though. And so in this first limit, the one at the top there, again, pause it if you want to think about it for a second. In this first limit, the highest degree term on the bottom is an x cubed. The highest degree term on the top is an x squared. And that's really the key, because when x gets really, really large, these other terms are going to be piddly and insignificant by comparison. They're going to be much, much smaller. And so, same thing down here. And so really all that matters when you're talking about what the limit is, like what we're approaching, is that lead term. And since the denominator has the greater degree, it's going to win, so to speak. So in other words, if you plug in like 1,000 for x, on top you're going to get 5 times 1,000 squared. 1,000 squared is 1,000,000. So you'll have 5 million. That's 5 with 6 zeros. And then you'll be subtracting 2,000 from it, and you'll be adding 3 to it. But that's still basically 5 million, right? It's 4,998,000 and change, right? So, or 997,997 actually. Anyway, that's the numerator. The denominator, though, when you cube 1,000, will be a billion, right? You're going to have 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Much bigger than the numerator. And so because of that, the denominator grows much faster than the numerator. The entire thing is going to approach 0. I'm just going to get this stuff out of the way here. So the whole limit is 0 because the denominator has the higher degree. And you might remember again from graphing rational functions, when the denominator has a higher degree, you're going to have a horizontal asymptote at 0. In the second one, you can look at those same set of rules that you learned. And again, you're looking at the degree again. Here, the numerator has the higher degree. Again, these other terms become piddly and insignificant when x gets really, really big in either the positive or negative direction. And so, because the denominator is not growing as fast now the numerator is growing faster, this whole thing is going to grow either toward infinity or toward negative infinity as x goes off to the left. And so you have to just kind of decide which one at this point. Now, in terms of limits, if the limit is infinity or negative infinity, it's also true that the limit does not exist. But since this is in only one direction, we can actually say which one it is. So what you want to do is you want to think, okay, when I plug a really big negative number in on top, because it's 2x cubed, right, an odd power, that's going to be negative on top. And on the bottom, it's x squared. So when I plug in a large value there that's negative, the square is actually going to make it positive. And so I have a negative over a positive. That whole thing is going to come out negative. Again, these other terms will not matter by comparison because those lead terms will be so much bigger. So it's going to be negative infinity over positive infinity, but the one on top's bigger, so the whole thing will approach negative infinity, which again, technically that limit does not exist, right? But by saying negative infinity, we give more information, all right? The next one here, if you look, they have the same degree, right? With the polynomial terms. However, there's also this exponential term, and that matters. Again, if you have an idea right now, pause and think and see if you can come up with the answer. And what happens is the exponential grows so much faster than the polynomial once x gets sufficiently large. Okay, sometimes it might take a while, but eventually exponential growth will beat polynomial growth every single time. Since e to the x will grow toward infinity as x goes to infinity, and it's going to beat all the other growth out there. This denominator is going to get much bigger in magnitude. It'll be negative because it's minus e to the x, but it's going to be minus a huge number and much bigger than the numerator will be. So the whole thing is going to approach 0. It'll be a little bit less. It'll be less than 0, right? It'll be a negative value because these are both, well, really it just matters the top one, right? This one will be positive and the bottom will be negative. But it doesn't matter because the bottom is going to be such a bigger number in magnitude, the whole thing approaches 0. However, something strange happens on this one because now the e to the x isn't growing as x goes to negative infinity. Instead, now you have e to a negative big value, right? And what happens is that's like let's say it was e to the negative 100th. That's equal to 1 over e to the 100th, which is almost 0. It's pretty much 0. This thing approaches 0. It becomes insignificant along with the rest of this junk. And now we're looking at just these two terms. They have the same degree. So what you have is 2 times a really, really big number divided by 3 times the exact same really, really big number. And so if you remember your rules from rational functions, when you have the same degree on top and bottom, you take the ratio of lead term coefficients, 2 over 3. And that's what we'll end up doing here. And so the limit here is actually 2/3. All right, I'm going to stop this one there. In the next video, we're going to look at some slightly more complicated problems where there's some square roots and other things happening to mix it up. And feel free to check those out too.